Hello everyone. We are coming to the next part of factors influencing vibrational frequency. The fourth factor is the hydrogen bonding. The presence of hydrogen bonding changes the position and shape of an infrared absorption band. The stronger the hydrogen bonding, the greater is the absorption shift from the normal values. The OH stretching bonds move to lower frequency with increased intensity and band widening. It is due to the fact that in a hydrogen bonded molecule, it is easier to stretch an OH bond because the strength of OH bond decreases as the hydrogen is attracted to the oxygen of neighboring molecule. The two types of hydrogen bonding, intermolecular and intramolecular, can be differentiated by the use of IR spectroscopy. The extent of intermolecular hydrogen bonding depends on the concentration of the solution, and hence the position and shape of IR band also depends on concentration. For alcohols and phenols at low concentration, a sharp band appears at 3650 cm inverse in addition to the broad band at 3350 cm inverse. The sharp band is OH stretching in free alcohols and the broad band is OH stretching in hydrogen bonded alcohols. Alcohols and phenols in condensed phases are strongly hydrogen bonded, usually in the form of a dynamic polymeric association, and this leads to a wide envelope of absorption and hence broadening of IR band. Hydrogen bonding involves a lengthening of the original OH bond, consequently weakened, and the frequency of absorption decreases. In intramolecular hydrogen bonding occur in enols, chelates, etc. and are particularly strong. The OH stretching frequency always will be less than 2800 cm inverse. Since these bonds are not easily broken even in dissolution or by an inert solvent, free OH stretching vibration will not get. Hydrogen bond may influence the CO stretching by frequency also, since due to hydrogen bonding, CO bonds may have increased single bond character, hence the length of the bond increases and frequency of vibration decreases. Next factor is electronic effects. The frequency and position of IR band is highly influenced by electron delocalization and the electronic effect of neighboring substance. For example, a neat sample of saturated aliphatic ketone shows normal band at 1715 cm inverse. The change in environment of the carbonyl can either decrease or increase the absorption frequency. That is, if we are replacing the R or R dash by a heteroatom, the CO absorption shifts, which depends on whether inductive effect or mesomeric or resonance effect predominates. First, we will discuss how inductive effect will affect the CO stretching frequency of ketones. Here, if the R is replaced by substituents having -I effects such as fluorine, chlorine, bromine, etc., the carbonyl absorption increases as the electron withdrawing group strengthens the CO bond, and the frequency of absorption increases, while the substituents having plus I effect will decrease the carbonyl absorption frequency. Since it makes a single bond character in the CO double bond. The resonance effect increases the single bond character of CO bond, which is the reason for decreasing the CO absorption frequency towards 1700 centimeter inverse in this case. The conjugation also has an effect on the IR band. Conjugation of a double bond provides single bond character through resonance, which lowers the frequency of vibration. Here, the carbon-carbon single bond gives the absorption band at 1670 centimeter inverse, but the conjugation decreases the frequency towards 1630 centimeter inverse. For carbonyl compounds, conjugation lowers the stretching frequency of carbonyl by 20 to 40 centimeter inverse. This is also attributed to the decrease in the double bond character of CO group by resonance. Let's take another example of acetophenone, which gives a CO stretching frequency of 1685 centimeter inverse. But if you are substituting ortho in the para position, a methoxy group, it decreases the frequency towards 1650 due to increased conjugation of OMe group with the carbonyl group, while the NO2 group in the para position increases the absorption frequency towards 1700 centimeter inverse due to the decreased conjugation. Next is the ring size effect. For this cycloheptene to cyclopropene system, the absorption frequency decreases as the bond angle decreases until it is minimum at 90 degrees. In cyclopropene, the value again increases. The reason is that when in the cyclobutene, the C-C bond and the C double bond C bond are perpendicular and the vibrational modes are orthogonal, so that it does not couple effectively. When the bond angle greater than 90 or less than 90, effective coupling occurs, leading to higher frequency of absorption. That is, as the angle becomes smaller, the coupling interaction becomes less until it is minimum at 90 degrees, and for cyclopropene it again increases. Coupling interaction also increases. In the case of cyclohexanone to cyclopropanone system also, the bond angle influences the absorption frequency of carbonyl group. In non-cyclic ketones and in cyclohexanone, the bond angle alpha equal to 120 degrees. Here, the sp2 orbitals forming sigma framework around the CO group can overlap perfectly with the sp3 orbitals on neighboring carbon atoms. As the bond angle decreases, there will be lesser degree of overlap, which introduce strain under the ring and a high S character outside it. It makes a high energy of CO stretching, and hence the frequency increases. These are the important factors which affect the vibrational frequency. Thank you very much.